Welcome to part 1 of our series in which we attempt to clone the famous watermelon game. By the end of the series, we should have created something that looks like this. This is what I have so far, and it's basically a direct clone of the viral game that all the VTubers and degenerates are playing. So yeah, let me get into a quick agenda of what we're going to be doing in this first edition of the series. All right, first we're going to have a brief JavaScript refresher. Actually, why don't we do this a different way? By the end of this series, by the end of this video, not series, we will have the bouncing DVD logo implemented on our browser. So maybe out of the scope of one video to implement the entirety of this game. So we'll cut a bit of scope, and by the end of this video, we'll hope to have some words maybe bouncing around the screen. Right? So the first part will be a quick JavaScript refresher. Then we'll have a history lesson. Quick, merciful, and then we'll have a physics lesson. Because the game we want to does have a significant physics component. And we're going to do the code. We're going to do the thing, do it. All right, so quick JavaScript tutorial or overview. What is JavaScript? JavaScript was a language invented in 10 days. I'm not joking, look it up, by the controversial Brendan Eich. I think that he went over to Mozilla after creating JavaScript for Netflix, or not Netflix, Netscape. And then he tweeted some homophobic stuff and got fired. So pretty funny guy. And he created JavaScript in 10 days, and now it's like the only language that anybody uses for anything. So there you go. It was originally supposed to be Scheme, which is a form of Lisp in the browser, and Lisp is basically the most minimal programming language that exists. It doesn't have any syntax really, it just has nested parentheses, which is awesome, honestly, and the world, if Brendan Eich had been allowed to use Scheme, would look a lot better in the world today, in my opinion. But alas, the marketers wanted something that resembled Java, to the point where they even named it JavaScript without it having any real connection to Java. So that's the background of JavaScript. What can JavaScript do? JavaScript is basically a scripting language for the browser. So, you know, you have your HTML stuff, and then you have your tab, blah, blah, blah. You have all your JavaScript can dynamically manipulate basically the inside of your HTML. So you can get it to change the text or move stuff around. But the biggest sort of challenge, not the biggest challenge, but a challenge for a long time has been, how do we get graphics in the browser? How do we get our games, our games that require a significant amount of physics and graphical rendering on the browser? So, well, the first option would be to use a div, right? So let's say this is a div, and then we give it some style, right? Blah, blah. Oops. And then you use JavaScript to manipulate the style. And you could do this for a game, a simple game, and that actually kind of works. But for the purposes of our tutorial and our clone of the watermelon game, we're going to be using the JavaScript canvas, which is basically an API for drawing. So now we're into the history lesson portion of our tutorial. What was JavaScript Canvas invented for? So note that JavaScript Canvas hasn't been around forever. I think it was like 10 years old or something. What were the problems it was trying to solve, and why does it exist? And why is it only 10 years old? JavaScript is like, I don't know, like 25, 30 years old now. But this API is pretty new. So what happened? Well, basically, there was first, well, I don't really know what I'm talking about because I was born after JavaScript, I think. But my understanding is that first you had like Java, if you wanted to do like graphics in your browser, first you had like Java applets. And these were like a disaster security-wise, and they were slow. And then you had Flash Player. And this was pretty polarizing. Flash Player was pretty widely accepted as what you would do if you wanted to make a game in the browser, and all your like favorite browser games from elementary school and stuff are probably made in Flash. Probably ended up using Flash Player. But Flash Player was a plugin, and that in itself is something that creators of browsers are and developers alike are really uncomfortable with an external plugin for creating graphics. There's a ton of reasons for why that's uncomfortable, and I'm not going to go into that. And now today we have the Canvas API. So what is an API? An API is just a set of functions, basically, a set of objects and functions. And what does it do? Well, it lets you, say, draw a rectangle on the screen, fill shapes, draw like a set of paths, maybe even draw curves, and draw circles. Now, I'll point out that this is not the only solution. With the advent of WebAssembly and WebGPU and all that new stuff, it's even newer than Canvas, you don't really even need JavaScript anymore. You can use a game engine that compiles to WebAssembly and then pull that in. So Unity, for example, does that. So does Raylib and other more simple game engines. But we're not going to go there for this the purposes of this project. I think that you can start. Canvas is a good place to start. And then if you start running into performance issues and you need to drop into like C++ for rendering or GPU rendering, then we can do that. But for the purposes of our little watermelon game, this is sufficient, and it really doesn't require any external dependencies. So the problem with WebAssembly, Unity, all that really nice stuff is that you end up having to pull and maintain like 30 different dependencies, Webpack, all that really annoying stuff that, in my opinion, is more than you need for a simple game. And note that for certain classes of games, you're actually completely fine manipulating the HTML. So by HTML, I mean there's some concept called the DOM in JavaScript, which models HTML tags or elements as objects in JavaScript, which you can then manipulate dynamically, and they show up right on the screen. So front-end frameworks like React basically are abstractions on top of this DOM. So all this stuff is abstract, and I apologize for that. We can get started. But first, I'm going to give us a quick brief physics lesson. So like I said, the watermelon game is a significant portion of the watermelon game is physics, so it's collision. So when one circle collides with another circle, it ends up not overlapping, right? They just stay next to each other, and they even bounce off each other. So a circle might bounce off another circle. Point is, that's not exactly what we're going to be implementing. That kind of bounce action is actually extremely mathematically complicated. But I think it's good to have some background on how sort of it gets to that point of complexity. Like, why is it so hard? I'll show you how it's hard. Well, I can just tell you that it's hard, or I can sort of start from the first principles and then build onto why. It's actually a hard problem to model the collisions of bouncing balls. So a particle in physics can have a position. So we we can model the world with a Cartesian coordinates. And a particle in our world can have some position. And it's like an XY. So let's call it X, Y. Now, the position is two numbers. Notice that there's two numbers in this position. And if you want to change the position, say by another two numbers, say you want to move it up to the left 2 units. So say I want to move it up to the left 2 units here to the new position. Let's just call it x prime, y prime. Well, the easiest way to do this is x plus 2. No, I'm sorry. X minus 2, y plus 2. So what we're doing here is we're adding two vectors. So if you're familiar with the concept of vector addition, it basically works how you expect it to work. So if you have a list of numbers like a, b plus c, d, it works the way you would expect it to. So you end up with a plus c, b plus d. So that works for position. So position kind of has this addition property, as well as subtraction property, and it has a scaling property. So say you want it to get closer to the origin by half. Well, it turns out that if you draw a line, if you want to get a certain distance on this line, then all you have to do is multiply x and y. So say you want to get exactly halfway, well then that point here is x over 2, y over 2. So scaling, or if you want to go twice as far, then this could be 2x, 2y. The scaling works how you would expect it to as well. Now, we talk about position, and position is a pretty graspable concept. It's pretty tangible. But velocity is a little trickier, especially in 2 dimensions. So let's drop down to 1 dimension. And let's just draw a number line. And your position on the number line is just one number. So no more vector anything, just a number. Now say the particle's here. Now in 1 dimension, a velocity can be positive or negative. And it can be some amount. So it can be some number of units. Like say this is a 1 in the positive direction, this possible velocity. And this particle can have a velocity of, say, 2 in that direction. So this is kind of doesn't really make much sense, but bear with me. So the way we kind of define velocity in our world model is that we say that every time step, and I'll explain what a time step is in a second, we add the velocity to the position. So if you've taken calculus or physics, you would know that position is the derivative of, velocity is the derivative of position. But in computers, you can't really model a continuous process. You can get really close, you can approximate one, but you can't actually model an infinite, because a continuous process kind of, each time step is infinitely small, and there's infinitely many of them. So you can't really model an infinite, or should I say, continuous process in a computer. But you can sort of approximate it. So it's not perfect, but it will do the job. So every time step means every, say 1 divided by 60 seconds, so that we can have 60 frames per second. We add our velocity to our position. So let's say the velocity is 1. All right, so in the first time step, so as t equals 0, 1, 2, our position is going to increase. So if we could animate this, you just see that our position goes up by 1 every time step. So then at time 0, maybe it's at 1, and then at time 1, maybe it's at 2, and then 3. So that's velocity. And what's really cool, and this is honestly blown my mind and I still don't really understand what works, but in 2 dimensions it works exactly the same. There's no change in this logic when you extend to 2 dimensions. So this is, to me, one of the more mind-blowing things in math and physics, is that you can extend the number of dimensions and everything stays the same. You just have to be careful to correctly define addition. And it seems like the way we do it, define addition, works perfectly well. So in 2 dimensions, your velocity ends up being 2 numbers, one in the x direction and one in the y direction. And then when you add those together, you get a velocity. So you have, say this particle's here, and then you can give it, say, a velocity of negative, say this is negative 1, 1. Or I'm sorry, say this is 1, negative 1. Now every time step you can say it moves 1 over. So that's velocity. It's the change every time step that a particle makes. So you can kind of see that it's adding some constant amount every time step. And hinting towards the next concept is acceleration, but we won't get into that this tutorial. So let's get into the coding part. I'm going to open up my text editor. So the really nice thing about JavaScript Canvas is that all you really need is a file system that looks like this. So your file system can just be project root. You can just have a project root directory. And then you can have index.html. And then you can have index.js. And that's it. You don't need Webpack. You don't need npm. You don't need config.ts as much as I do like TypeScript. This is all you really need for a Canvas project. It's really nice. Okay. To our code. So now on the left panel I have HTML, and on the right panel I have JavaScript. By the way, I use Emacs. I don't really know how to use Emacs, but I'm learning how to use Emacs because I haven't had sex in over 5 years. So we are going to just write out our HTML. It's pretty simple. The canvas element has a couple properties. It's going to have a width and a height. What is going on with the width and the height represent the coordinate system of the canvas, so I'll explain what that means. So let's just say width 480 pixels, height 640. So in our canvas world, the coordinate system is a little goofy. It's going to run with the y-axis going down. So this is a positive y, and this is a positive x. And this is going to be like the height. This is going to be the width. And this is going to be the visible this region. Okay, so going down, y goes down. It's a little strange, but you get used to it. And I want to close up this tag. Whoops. I believe if you resize the canvas with CSS and override these height and width, you get like a stretched resolution. But the internal rendering resolution is the same as the width and height, I believe. I could be wrong about that. So let's just add an inline style of border. 2 pixels, solid black. And then let's also add some basic. And then let's add an ID. So let's talking about our document object model, or DOM, or DOM. The DOM basically allows you to treat an HTML tag as an object in JavaScript, do stuff to that object in JavaScript, and have it reflect in the browser immediately. So one way to do that is having the ID. There's a quick and dirty way of getting a particular HTML element by its ID. So we can just go const canvas equals document.getElement by ID. And I have not set up my I've not set up my autocomplete map, so weird stuff is gonna happen, but bear with me. Make. Okay. And then what we're gonna need to do to make it render is we're gonna need to give it a context. Canvas context 2D. And then for the sake of this tutorial, we will draw a quick rectangular box. So let's utx.fillRect. And hey, you can see right here that the API goes X number, Y number, and I can actually click the reference and it will give me there. So fillRect, XY width height. So what do we mean by XY width height? Well, X and Y, we have a coordinate system here. The rectangle at X and Y with the width, height is going to be rendered like that. So it's a little strange to think of rectangles in this sense. Usually you would, I sort of intuitively think of a rectangle as best determined by its center, but in this API, upper left, and then a width and a height. So let's just say upper left is 100, and then our height is going to be 50, and then our other height is going to be 50. Let's see if this worked. Let's open up our thing in the browser. I don't see it. I believe that's because either we have an error or we don't have a fill color. So we're going to want to do utx.fill style equals, and then we'll do dark black. All right, and it's still not working. It's a little strange. What did I do wrong here? Whoops. What I did wrong here is I forgot to call the script into the HTML. So you gotta do that. And put it at the bottom of the body. Just to make sure so one quick gotcha is that you have to put the script at the bottom of the body, otherwise you will run the risk of this running before the element with that particular ID exists. So you're gonna wanna either specify in the index that wait until the body is loaded, or we can just put it at the bottom. I think for ease of our tutorial, let's just put it at the bottom. So you can see our canvas here, and now you can see our ball. Great. It's a little strange. The canvas looks like a total... Oh, I'm sorry. I should be 640 by 480. All right. Now we... All right. So now you can see this little box. Now the question is, how do we want to animate it? So if we do try to animate, we could use a while loop, and then we could do stuff inside, but I prefer the suggested method, which is to make a function called update or render or something. So call it render. So the new way of doing functions in JavaScript is this arrow notation, which is a lot cleaner, in my opinion. So you can have arguments in here, and then you have the block here. As opposed to like, you know, it's pretty similar, but oh no, you don't even have, or you can do that. Well, there's 3 ways of doing it. There's this, and there's also, I'm sorry, function render. Don't ask me what the difference between these are. I don't know. And then what we're going to do is we're going to put it inside. And then we're going to run it. All right, and in this, we're going to actually recursively call itself with the window. I think window, one quick thing in JavaScript is that window is a sort of general purpose object that represents properties of the browser window, like the height and width of the browser window, how to close and open tabs and stuff. But I think for some window properties, it actually pulls into the global namespace, so you don't need it. So I can just say request animation frame, and then the callback is itself. And now this thing is a little bit devious because it thinks its frame rate to your monitor refresh rate. So if you think for a second, that might be a bit of an issue because a 144 hertz monitor will have far more updates, far more render updates than a 60 hertz monitor, which will change the behavior of the physics significantly. And as it turns out, it's not a trivial thing to solve. I wish it was just like one line, like I could just go like 60 to lock to 60 FPS, but sadly that's not the world we live in. To explain why, it would be a bit of a tangent, so I won't go there. All right, so in our render function, we're going to want to first clear the screen. So we're going to clear the screen with a big rectangle, and then we're going to go canvas width canvas. So why does this work? Remember, this width and this height correspond directly to this width and this height. So you can see how the document object model works. These properties correspond directly to these properties in HTML, and you can change them, and they'll immediately change in the HTML. So it's pretty cool. That's basically JavaScript in a nutshell. Canvas.width, canvas.height. So yeah, so if we wanted to change the, say, height equals 0, equals like 10, we could, and then I'll show you all of a sudden now it's really, really short. So it works. Whoops. It works. Whoops. I messed up. What's width and height? And then why don't we clear it with a black, and then let's draw a white square. All right. Boom. Okay, so now let's get this thing moving. Okay, so this is how I like to program. You start without any variables at all, and then you extract out variables and you make them belong to outer and outer scopes. So we start with the variable here, and then, so x, const x, well, it's not a const because we're going to be changing it. So now that becomes x, right? And let y equals 200, and that becomes y. And now that we want to change it every frame, say we want to move, say let's move it by 1 every frame. Now we're going to actually put these out here. Oops. So let's see. Now we have it animated. Very good. Now we got to get the bounce going. So let's abstract a bit here. Remember we talked about vectors? Well, why don't we make a position vector? So let's say let position equal. This is one thing I don't really like about JavaScript, is that it's not super easy to go from variable to object. You have to change quite a bit of syntax. Right, so a good programming language lets you evolve your code more naturally than this. An example of this is, I guess, Rust, where you can have your structs sort of use the same syntax as your variable declarations. Or maybe not Rust, actually, but I wish the language did that. And then we can further, remember when I talked about velocity, we can further track that by saying velocity equals 1. And then, so now position.x. Position, and then now. All right, now prove to ourselves that it works. Still great, perfect. All right, so quick aside. In a lot of languages, you would be able to overwrite the plus operator, and you'd be able to change this to position plus equals velocity. Sadly, in sadly in JavaScript, there's no way of doing this. So if we want to abstract out this vector addition, we have to make our own function. So let's just do that. So constant vector add VW equals, whoops. return v.x, oops, return x, v.x plus w.x, and then, whoops, y. I need to learn more Vim commands. And then we would have position equals v-add, position velocity. So this is a good level of abstraction for our problem. Just confirm that works. So now we want to get this bounciness. So let's return to our physics lesson. So how does bounce work? Well, say here's our boundaries, and say here's our particle, and say the particle's velocity, in other words, the amount it changes every frame, is this +1 + 1. So we can say the velocity equals +1 + 1. So here's the particle and its velocity. So what you can kind of do is you can kind of project it onto the wall. You can kind of see that it hits the wall on this particular velocity. And then you want it to exit the wall in that way, so that this angle is the same as that angle. Well, you don't have to get into too much geometry, but basically you want it to be symmetric. Okay, so now how do you know what that looks like? How do we change the velocity when it hits the wall so that it's kind of symmetric and it bounces off? Well, in this case, we can do a little trick. So here's our old, we can call this our old, we can call this our new, right? Let's put them at the origin. This is old, and new is going to be that way. So it looks like what we're doing is we're reflecting across the y-axis. That means the x is the same. I'm sorry, the y is the same, right? The x changes. So now the new velocity is going to be -1. This guy is -1, 1. This is 1, 1. Okay. Now you may see that the way this changes actually is different on each wall. So say you're going this way. Now when you hit the wall, the new one's going to be that way, right? So hit the wall like that. I want to exit the wall like that. We can do our same trick and say this is our old, and then say this is our new, and then we can put them together and show that, oh, now we're flipping across the x-axis. So now it's the y coordinate that changes. So it turns out that the right and the left walls have the same behavior. The top and the bottom walls have the same behavior. I'll let you figure that out yourself if you don't believe me. But now we have some idea of how to change the velocity upon collision. Problem is, how do we know when the collision happens? Well, with a rectangle centered at x, y, w, h, right? This is our rectangle. Let's draw a rectangle. This rectangle has some properties, x, y, w, and h, right? And this screen has some properties too, where this point is 0, 0, and this point is 0, height, canvas.height. So we'll just call that height. This is the width height. And this is width 0. Now, there's a bit of a puzzle. The puzzle is figuring out exactly what conditions need to be met for each of the possible collisions, the top wall, the bottom wall, the right wall, and the left wall. So I won't write them all out here, but you can kind of see how a pattern may arise. And I might not be able to do it off the top of my head without flipping back to this diagram. So bear with me. All right. So we have our position, our new position. Now we want to check to see if it collides with the right wall. Say right wall. So right wall would be, colliding with the right wall would mean this right edge touches the right wall. So if it touches or goes beyond it. So that means the right edge is x. Well, I actually forgot one thing. We haven't really defined the height and width yet. So like I said before, it's like to start local and then move out. So let not just move out, but also become more abstract. So we start with some concreteness and then move to, okay, we see this clump of variables now. We see these two variables. This should be a vector. So now, I'm sorry, not a vector. This could be an object, right? Equals W50. Ah! No, I'm just going to do it. 50, and then, well, it looks like our position maybe should belong to this rect. But I don't really agree with that. I think the rect and the position should be somewhat. So you see what I'm saying? We could embed this position in the rect, but I don't really want to do that. I want to keep the rect separate because this is constant. This will never change now. And now instead of W and H, we'll say rect W and H. Maybe in the future we might change though. Change our minds here. So now I'm actually disagreeing with what I just said. I said that we should keep these variables separate, but the particle in physics sort of has all the properties kind of belong to itself. So its position and its velocity should be properties of itself. So just change our minds here. Oops. Velocity. Just have to make some changes. Rect that position at x. Rect that position at y. Rect that velocity. Rect that position. So now it's no longer constant though. Well, actually, I'm sorry. So JavaScript doesn't work the way you think it does. If you have a constant variable, you can still modify fields and nested subfields. The constant really only prevents you from saying, redefining the variable name, so rect equals. You can't do that. But you can modify it in place, which is what we're going to be doing with this line here. Rect that position equals bad. Let's just make sure everything still works. Okay, it does. Now we're going to want to check for the collision with the right wall. So right wall collision, if rect.x plus rect.w greater than or equal to canvas.width, that's a right collision. Now for the left collision, if rect.x less than or equal to 0. And rect.y is less than or equal to 0. Rect.y plus rect.h greater than or equal to canvas.height. So we have these four conditions, and remember what I said, that the top and bottom act similarly, and the right and the left walls act similarly, so we can put those together. Now, what did we say how the velocity changes? So the right wall, the x changes. So rect.velocity.x equals rect.velocity.x negative. So negative. And then here the y changes. I believe this is right. If we're wrong, we made a mistake, then we can simply flip those. And let's see if it works. Okay, something went wrong. What did I do wrong? Did I say this x should be y? Very strange. What did I do wrong? Maybe that's what I did wrong. Well, right now we're only hitting the right wall. Start, so we can just practice with the right. We're only hitting the bottom wall. Okay. Very odd. What did I do wrong here? Let's comment the bottom out. Oops. Come on, let's top out. So the condition that we're trying to meet is rect.y plus rect.h is greater than or equal to canvas.height. Okay. Well, let's see if the condition's met. Let's do a console log. Condition is not met. If something is... you know what I'm doing wrong? It's rect.position.y. This is why you use TypeScript. Because JavaScript won't even tell you that something is... the key doesn't exist, it'll just give you null. So it's very annoying, like JavaScript where you say you have const v equals this, v dot foo. Well, that's going to be null, I think. Or maybe undefined. Null and undefined in JavaScript are slightly different. Forgot which. But point is, it's kind of ugly. That's one of the things I don't like about JavaScript. It should give you an error, but it's okay. Okay, so position. Position. Okay, now let's check it out. All right, there we go. I think we can crank up the velocity a little bit. Let's crank it up to 3. And what we're also going to do is we're going to add some DOM elements to manipulate this, just for the DOM tutorial here, just to get familiar with the document object model. Okay, so what I mean by that is, let's say you want to increase the speed, right? So let's add a button. Increase speed. Okay. So let's give this button an ID. Equals increase speed. So now we have this button, increase speed, and hopefully this should increase the speed. So what we're going to do is we're going to say, how do we get this button in our code? Well, we're going to say document button equals increase speed button. Document get element by ID increase speed increase speed button dot onClick. So now we're setting the onClick property, and we just need to give this a function. So this function will now run whenever the button is clicked. So I can prove that to you. Before we add any logic, let's just say alert world or something. Okay, so that did work. And then we're going to say increase speed button on click is rect.position, rect.velocity that x plus equal, let's just say plus 0.5, and then y as well. Hey, why don't we say v add, huh? Just be cute here. That velocity. And then let's also show you how you can manipulate HTML text. So we're actually not going to add any other elements here. We're just going to manipulate the text with a property. So now we're going to say increase speed button dot inner HTML. I don't really know what the difference between inner HTML and inner text is. It has something to do with how HTML tags are rendered. So if I give it like an A, or if I give it like a bold or something, this will work. But if I do inner text, this won't work. So something like that. But inner HTML property equals sets to increase speed, and let's actually say the speed. So let's say how do you text interpolation in JavaScript? It's kind of weird. I think you can use this, if I'm not mistaken. And you can go speed. And then our speed is actually going to be the magnitude of the velocity. So not necessarily the individual components, but the square root of the square of the individual component. So like Pythagorean theorem. So speed equals, so that way speed will always be positive no matter whether the velocity is negative. It's a little, it's like absolute value. So equals math dot square root rect dot velocity dot x times rect dot velocity. A lot of typing, and then rect dot velocity, the line here, v dot y and rect dot velocity dot y. I'm really slow. Okay. Hopefully that works. All right. So seems like we're not increasing. Seems like what's happening is very strange. And it seems to be going back to the speed it wants to go to. So what's going on here? What is going on here? Why is our speed going down? Very strange. What is going on? Oh, well, part of it is this speed isn't correct. This is in the speed plus. You add them. And then why is this happening? Why is the velocity going crazy here? Very odd. Well, it's kind of working. I'm not sure this is what I expected it to do, but this is what's happening. Let's just check the rect. So now in the console, you can actually check your object. So velocity. Now it's -1, -4. Ah, I know why. It's because we're increasing it even if it goes negative. Because remember our velocity here can become negative, and then why would we increase it here, right? That doesn't make any sense. So why don't we, instead of increasing it, let's scale it. So remember what I was saying about vector scaling. This way, we do want to preserve the sign, actually. So my initial... So let's work backwards. So whatever scale, and let's scale it by like 1.5, 1 point. I don't really know, 1.5. And then let's define v scale. V equals vc. And then that ends up being return x, e dot x times c, y, e dot y times c. Okay. Now let's see if this works. There we go. Oh, now we're talking. Okay. Alright, well that pretty much concludes. Well, I promised we would do DVD logo bounce, so why don't we show some of the other rendering capabilities, such as rendering text. Rendering text is always going to be useful. Alright, so instead of filling this rectangle, or we can fill a rectangle with some text. Let's see, fill text. Okay, so fill text is, again, if you look at the API, it's text string, x number, y number, max width. Okay, so I guess that'll truncate it if you want a maximum width. So let's just say DVD, and then let's say rect dot position dot x, rect dot position dot y. Now we're gonna want to do one thing. We're gonna want to change the fill color. So let's fill style, and let's just make it, I don't know, green. Ooh, this is something that we can actually change as we go. So that'll be fun. We can try changing. We can try doing a color effect for giggles. But for now, let's just keep it like this. So let's say FF000, whatever that ends up being. Maybe red. Okay. So let's see if we can get some. Oops. Oh, I can see it, but it's very small. Let's make it a bit bigger. And it seems like the text bottom right is there, so we can add some offset. Let's just add 20, and we can figure it out. That'll be more sets later. So I don't actually remember that's what I do remember. Prefix font equals 32 pixels sans 0. There we go. So now let's add a color effect for shits and giggles. I don't really know what the color effect is here. Let's see, what is it? It looks like every time well, it looks like the color is changing. No, every time it bounces, the color changes. Okay, so that's should be pretty straightforward. We could, I don't really know how to manipulate colors with JavaScript, so let's be lazy and just say color, possible colors. Let's just make a list of them. So a list of color objects, it'll just be strings of some type. So, well, I lied. Let's do this programmatically. It will be fun. So, this is kind of annoying, but we're gonna add like 100 different colors or something. So we'll 0 as less than. I don't know exactly how we're gonna do this, but we'll let number. It's not gonna be counts. It's gonna be that. And then we're gonna add some of the possible. Let's do this. So const no segment or no hex values. So we're gonna take a random hex value and then we're gonna append that 3 times. So let's just say ff 00 something in between, like say I don't know 33. And we're just going to make a bunch of random ones. Obviously, not perfect, but this will have to do. So, I want to just do it 3 times. Oops. K is 0, K plus plus. We're now going to append a color hex value. X value is random, so then this will be map.floor. So that's how you would get a random element in the list. Map.floor, map.random times X values that one. So this guarantees a random of the say colors. What's it called? So add and push to add. Let's see if this worked. Okay, now we have a bunch of random colors. So every time it hits, now we're going to want to change the color. Let's make this bold. Let's see if I can make this bold. Nice, okay. And then well, we don't have to actually offset the X, we can just offset the Y for now and figure out the rest later. Okay. So now we're going to want to change the color every single time it hits. So there's no one way to do this, but I'm just going to make a flag so it did hit. Okay, so now if it hit, then, so let's add another variable here, color. So starts out as red. Oops. Red.color. So let me explain what's going on here. Actually, I should have done this earlier. Not bad. But the CTX is a drawing context that we get from the canvas DOM node, which is this thing. You have to get the context out of the canvas. It's a bit of a mouthful. And then this context has context global, attributes like the fill style and the fill color. And what you can do is you can change them, and then you can render something, and then you can change again, render something else. So that's how you would render different objects. So you don't need to actually, in the function that renders the object, you're not actually specifying like attributes like the color. It looks at the global color of that context. So that is nice in a way that there's not as much, not as many arguments you have to pass to the functions, but you just have to be careful. And there's a nice thing called ctx.save, I believe, and ctx.restore. So then you can kind of have a stack machine of the different states. So you can, the save saves it to a stack, and then restore pops the latest one off the stack. So that way, if you do want to do a subroutine with a clear and then change all the and change like a bunch of random globals, you know which ones you want to change back. You can just wrap it in a save and restore, and it should work. But that's actually very nice. So DVD, okay, so rect color, and then now we're going to change the rect color if it did hit. So now rect.color equals colors math.floor math.random times colors.ring. And that is a mouthful, but it's got to be done like that. Okay, unless we want to extract this, maybe it's time to extract this out to a function because we've called it twice. But, what happened? Colors.length is not a function. I like how every programming language has a different way of specifying length of an array. It's pretty funny. Now, we've got some pretty booty cheeks colors in here, but, well, there you go. So that's done. Yeah, that's pretty much it for this installment. Next installment, we'll talk about how to get things to bounce off each other. All right.